Okay, thank you very much, Stefan. So I want to start off with the NAMUR architecture today and how we implemented it in the past and how we want to implement it in the future. My name is Sebastian Böse. I'm part of the process industry management team here at Beckhoff in our HQ in Ferl. Yeah, let's start off with NOAA itself. A couple words about the NAMUR architecture. So the idea is to gain more information out of the field devices, by using or creating a so-called second channel. So the idea is to get so-called vitality data out of the field devices, which represent the status and the lifetime of the field devices and are not really responsible for the process itself. So these data won't be connected or won't be sent to the DCS, but more to an asset administration or asset management tool. So this is the general concept behind the NAMUR open architecture, which is standardized or implemented in the NAMUR general recommendations. Then I want to talk about the brownfield today. So more or less, NOAA focuses on the brownfield, where we have, for example, Modbus, Profibus, RS232. We also have a couple of hard devices down there. And I also added here Ethernet APL and Profinet because that's also something that's getting more and more important. And we also want to have a look at that and how we can implement and interact with that in the NAMUR open architecture. So I will show you a couple of architectures that we've implemented and that we want to implement or currently implementing, on how we accessed the additional data from the field devices and how we then send them up to the higher level systems through OPCDI and the PADIM. So this is really the maybe simplest architecture for us. So we got a field device in the hazardous area, have then a signal splitter like an barrier, for example, which already has two outputs at the upper level. So one output is used for the 4020 milliamps to the DCS, and what we've done in the past, for example, with Bayer, is that we use the second channel of the signal splitter connected via an hard terminal and then just read out the data from the field device and presented it via PADIM via OPCDI. So like I said, this would be the really simplest architecture. But we also can have like this architecture where we don't have a signal splitter with two channels. That's where we created a special terminal for that, where we can directly connect us to the two wires inside of this cabling, and then can act as a hard secondary master. So that's what we've tested in the past and already also implemented as another way to get information out of hard field devices or 4020 milliamp and hard field devices. Now, if we do not have a signal splitter, it's the same way. So we can also do that if there are no hazardous areas. We can also implement this architecture for hard field devices. I will later talk about all the hard commands and so on, how we access the data really, but I want to show you here the architecture behind. Now we are switching to a fully hazardous area DCS as well with already intrinsically safe inputs, but we also want to access the hard data here. So we can do that as well. This is something we want to implement in the future. We haven't done that in the past because that means that if we also connect directly onto these two wires, that we need additional calculations in terms of the intrinsic safety. So that's not so easy to do. And it's also because NAMUR and the NAMUR architecture is something what we want to add while the whole process plant is still running. So we don't want to interfere or touch the existing system. And if we do something like that, we're really touching the intrinsic safety and the proof of intrinsic safety. So technically it's possible, but it's something that we really need to consider if that's something we want to do or if we want to touch this intrinsically safe loop. But just to show you that it's also an option for us. What we've also done in the past are some other protocols, for example, Modbus. We've also done it. So in this case, the field device is externally powered, for example, 4 to 20 milliamps or whatever, and get a Modbus communication port as well on the device. This is typical for analyzers for huge applications or huge field devices, that they have an additional second channel for parameterization or for accessing the device and diagnostics and so on. And this is pretty easy for us then also to use this second channel, or to build up this second channel basically by using this Modbus TCP port, or for example the RS232 port. This is something we already did in the past as well. Of course, we can't access that many data through RS232, but yeah, it's enough to get the general status out of the field device and present that in a cyclic way through this standardized information model. We've also used Modbus RTU in the past, so this is both theoretical communication, which makes that pretty easy for us, again, to utilize that. Now switching over to some more special applications, or something that's not so easy to do. So in this case, we get a field device connected via 4 to 20 milliamps and hard to the remote I/O station, which is a Profibus remote I/O, and it's also intrinsically safe. That means that we can't touch the system, or we won't touch the system below the remote I/O. What we want to do is connect us to the Profibus network and access all the field device data through this remote I/O. For that, we used a gateway, so we've did that or currently doing that at some test beds. We used a gateway, and to this gateway, we send all the hard commands through OPCDI methods. So the exact same way that we did in the direct connection to all the hard field devices, which I showed in the first slides. We send the same hard commands here via OPCDI to the gateway, and then the gateway maps that onto the Profibus and onto the remote I/O, so that we can access all the field devices below the remote I/O. So this is not that easy to do. We're currently working on that, but it's also a way of how to implement in your open architecture and how to get this PA-DIM filled with data out of the field. Then I'm already at Ethernet APL. So this is something which is really getting more and more attraction right now. Mostly maybe for greenfield plants, but we can also do that in brownfield plants if we add Ethernet APL first, and then we want to focus on the NAMUR architecture afterwards. So this could be an architecture where we have a field switch, which is connected in a Profinet ring to the DCS, and under it we have the Profinet field device. And what we want to do here is, for example, we can use just a standard switch in the Profinet ring, connect our device there as an maybe a Profinet sniffer, whatever. This way, like access all the data that's in the Profinet ring, or access the field devices over Profinet in the whole network, and then read out all the devices like you know from shared device Profinet. So this is what we've also focusing on right now. And then at the end, it's always the same information model via OPCDI what we want to show to an upper level system. So that's the main benefit, or the main message, that we always show the same information model, whether it's fully filled or just a few variables, to upper level systems, whether it's an pH sensor or an O2 sensor or whatever, and independent from the manufacturer as well. This is also an option, just to show you another option that we can implement, like directly put a remote station with a controller in the field, and where you directly can access the PA-DIM over OPCDI from the field, which makes it easier to just have one device in the field and do not have a switch and a second switch and our field device, our edge device. The main benefit here is that we can also utilize hard in the same terminal string there. So this was the last architecture that we've implemented or we've focused on. So if you have a look back at all the brownfield protocols and all the technologies that are out there, so they are all accessible and usable for NAMUR architecture. I mean, some of them like RS232 are really not that many information that we can access out of the field device via HART. It's more or less all of the data in the PIDIM that we can fill. And it's the same with Ethernet APL and Profinet. So there are more and more data available than via RS232, for example. But the main message is that we can access all of this, that we can get a benefit out of that, but only if we do it in a standardized way with a standardized information model. But like I said, standardized information model, we always want to fill this PADIM. It has been standardized for 1.1, and I think it was in February, for process analytical devices or devices from the process analytical technology department. And for example, these are pH sensors, these are O2 sensors, TOC sensors, whatever. So more complex and analytical field devices, and they all have the same information model. All this PADIM. I've just put in here a screenshot of the OPCDI server, how it looks like or how it should look like at the end. This is a screenshot of our OPCDI server itself. So we have the standard part upwards with some, which was implemented in PIDIM a few years back, like manufacturer, model, serial number, software version, and so on. So really standard parameters that are applicable for like every type of field device. And then we have the really focusing parameter set, the pH device under it. So this is how a signal set of all the parameters for a pH sensor looks like. And we need to fill that. And how to do that is, or the main question is here, where to find the data on the field device. So like I said, I'm going back again. So for example, where to find this raw value, where to find the operating hours counter, and so on. And what we've did is for these existing field device protocols that we created a database where we put all the information in. And for example, I've put it in here for an HART command. For example, if you want to access the serial number, we need to know which HART command we need to send, which write data, which write lengths, and so on. So all the things we send to the field device. And then we also need to know in this whole byte array that we get back from the field device where to find the information that we want with an offset, with an length, and of course the parameter type or the signal type itself. For example, this here is Latin 1 then. So then we know how to convert it, how to map it, and how to put it onto the standardized information model. And this took quite some time to fill out this data sheet, this database. We used EDDs, we used the data sheets itself from the field devices to fill out this or fill in all the information that we can really reach all the data from the field device. So this is what we've did for a few field devices that our customers wanted us to integrate, but we are currently working on filling that more and more and do an automatic way for that to fill this database. For Ethernet APL and Profinet, it's a bit different. I mean, if we use Profinet profiles, it's already possible to switch field devices and have a standardized view on all the parameters that are accessible. If it's not the case, then we need to do the same within database and to know where to find all the variables. And with Ethernet APL, there's also coming the option of a web server or a user interface, for example, with the FDI. So that would be also an option in the future, but then it's not too easy to map from a web server onto a standardized information model. So the web server is really more for maintenance purposes, maybe, but not for an like cyclic analysis of all the field devices and their statuses. But this is how we've implemented that and how we accessed all the data in the field. So in short summary, we've did a couple of these implementations in the past. They worked pretty well, but of course there are really, really many out there which we need to implement in the future. For example, do this whole Profibus setup, finish that. We've also want to use Modbus TCP in the future. or maybe directly connect through OPCUA or Profinet through Ethernet APL to Ethernet APL field devices, which is also an option in the future. So this is something what we need to do, but we are in a good way right now to finish all this, or to build up this whole NAMUR open architecture for all the existing field devices down there. Last but not least, our goal, like I said, in the future is to combine all of that. So we do not want to have a field device just for an edge device just for hard. We've also want an edge device which can do in the same way RS-232 or Modbus or Ethernet APL at the end. And then we want to build up one OPCUA server which collects the data, or which shows the data from all of these different field devices in a standardized way through the PIDIM. And this is the last thing I want to talk about today, which is building up this PIDIM at the end. So this is already another screenshot, for example, from a Liquiline here, which we implemented or which we connected through the HART protocol. And the main point is that we also want to do a standardized way of presenting it in the OPCUA server. So there are two options. The easiest option would be that we just put all the variables that we have in the PLC in our controller to OPCUA, so that the end user or the customer can just access all the whole set of data and needs to search for each and every parameter for himself. Like I said, it would be the easiest one, but we chose another one. So what we do is that we touched or really create a node set file, which is then loaded into the OPCUA server. So the workflow looks like that we also, for example, for hard devices, we send in standard commands to get a response from the feed device, to know which type of device that is. And whether it's a PH device or an O2 device, the signal or the parameter set is a bit different. So we added the node set in our PLC. We added the whole node set, so it's an XML file at the end. And then we load that into the OPCUA server, which is also running on our controller. And then we have the standardized information model in a really simple way. Do not have any variables that aren't filled in or that aren't used in the PIDIM, so that the end user and the customer always have the standardized information model for all the field devices that are really connected. And if there's no field device connected on channel 16 or whatever, then there's no data set in the OPCUA server. So that's the goal at the end, or that's what we achieved in the past, that we always have this completely filled or this completely standardized server itself with all the PIDIM information models, to make it really easy for the customer, and that's what we've did here with OPCUA. Yeah, that's it from my side. So thank you very much for listening. I think the questions will be at the end of the whole session, right?